is by Christoph Plefka. Well, we're going to talk about the quantum AdS 5 cross S5 superstring in light cone gauge.
Right. Is there a pointer, a laser pointer somewhere?
Was.
There's a stick there.
Stick. There's always a stick.
Stick is also fine. Yeah. All right. Good. So yeah, this is the title of my talk. But before I wanted to get started on the talk, I wanted to share a curious comment with you on numerology concerning the for-loop condition anomalous dimension, which is of intense interest these days. I just wanted to sort of point out that there's a toy model which shares many, unfortunately not all, properties of maximally supersymmetric Yang-Mills theory in 4 dimensions, namely this plane wave matrix model, which arises in a compactification on a free sphere. Well, that is for super Yang-Mills, and then you end up with a rather compact supersymmetric gauge quantum mechanical model, which has an SU2/4 supersymmetry, and this model has an SU2 subsector, just like we have in n=4 super Yang-Mills, and its spectrum has actually been computed in this subsector up to 4 loop orders in a very old paper, 3 years old now, together with Thomas Fischbacher and Thomas Klose, who's also here in the audience. And so it's unfortunately it is not true that this model is generally integrable. It's at higher loop orders. It's not integrable in larger sectors, but in this closed minimal SU2 rank 1 subsector, it is integrable up to 4 loops. And there's a set of beta equations, asymptotic beta equations, describing the spectrum here, and it is structurally very, very parallel to what we have then later on learned in n=4 super Yang-Mills, namely it is also dressing factor 3 for the experts up to 4 loop orders, and at 4 loop order you have to include a dressing factor, which also breaks the BMN scaling at that loop order. And moreover, you can see in this 4 loop study that this wrapping effect is real, namely that if you compute the first state which is affected by wrapping, this so C and W are now complexified scalars of this. Well, there's a set of 6 and 3 scalars. So this is the sector which arises from compactifying the 6 scalars of the n=4 super Yang-Mills, and then the usual Z and W complex combinations. So here you see the result for the 4 loop scaling dimension. Well, in this case, it would be the energy shift of which you get by naively applying the beta equations, and this is the real work, the true value which you get when you really compute this shift. And now just comparing numbers, it is quite amusing. Well, first of all, it's true up to 3 loop orders that these numbers are exactly the same. At 4 loop order, they start to move apart. And of course, because we only have a finite number of degrees of freedom in this quantum mechanical model, not forgetting about this large n thing, there are no nice transcendental numbers kicking in at this loop order. So the phase factor doesn't have such a transcendental number contribution. But if you look just at the naked numbers, they're all in the same ballpark. And just yesterday, I had this little idea together with Thomas to just compare these numbers. So if we take, I'm sorry, I didn't tell you. So there is this conjecture due to Kotikov, Lipatov, Rey, Staudacher, Velijanin for the 4 loop scaling dimensions. And this is the naive value you would get if you would just solve the asymptotic beta equations. And if you now look at these fractions, conjecture over naive value, exact value over naive value, you see that they're pretty much the same. So just a nice observation. So good. But now to my talk. So yeah, now to something completely different, to the quantum AdS 5 superstring in light cone gauge. And this is more or less a summary of work I did in collaboration with Gleb Arutyunov, Sergei Frolov, Maria Samakla the last year and this year in a paper together with 2 of my students, Alexander Henschel and Per Sundin. Per is also in the audience. Good. So the plan is that I'll first, in order to introduce you to the setting, I'll discuss the bosonic AdS5 cross S5 string in a uniform light cone gauge in a first order formalism, and then comment or briefly guide you through the supercoset approach to the superstring in order to include the fermionic degrees of freedom and its light cone gauge, and how you can extract in the near BMN limit the free and the interacting pieces of its Hamiltonian, and then compute its spectrum in certain subsectors. So this is what we have done in the paper this year. We computed the spectrum of that near BMN limit Hamiltonian in larger subsectors, and confronted the result with explicit solutions of the set of nested beta equations which should describe it, and we found agreement in all cases, which I'll show you. And then finally, if time allows, but I'm not certain that that will be the case, I might also discuss how the centrally extended SU2/2 plus SU2/2 supersymmetry algebra arises here in the light cone gauge string formulation. Good. So let's start. AdS5 cross S5 metric in global coordinates. Just to set notations, we have the z's, which are the transverse coordinates in the AdS5, and the y's, the transverse coordinates in the S5 piece of the metric. It has two obvious isometries if you shift t and phi, and the associated inertia charges with these symmetries are exactly the space-time energy and an angular momentum on the S5. And moreover, you have four charges which are well known by now, S1, S2, which normally refers to as the spins, and J1 and J2 as the angular momenta on the S5. It's the closed string action in this background is spelled out here. So up front we have the effective string tension, which is the ratio of the radius of AdS5 and S5 over the string length squared, and it is of course to be associated with the Toff coupling in the gauge theory. Moreover, the length of the string, the extension of the space-like coordinate sigma on the world sheet is kept open here. So I'll just introduce the parameter r, and gamma is just this combination of a world sheet metric whose determinant is -1, x are the embedding coordinates, and g is the metric. And of course we have the fermions, but for the beginning let me suppress the fermions. So what I want to do now is I want to rewrite this action, up here it's again, in a first order formalism. So I first compute its momenta. There's a little tricky definition of square root of lambda here, which is not necessarily standard. And then you can rewrite the action in the first order form depending on p and x dot, depending on x dot only linearly in this manner. And here you see very nicely how the world sheet metric gives rise to constraint equations, which are just these two bracketed expressions. C1 is the first constraint, C2 is the second constraint. If I now look at the equations of motion for P of this S tilde action, which are algebraic, solve them, plug them back in, I end up with S. Just convenience. You'll see it. Good. So I already mentioned these two conserved charges, the energy and the angular momentum J. And what one does now next is one introduces light cone coordinates by choosing exactly the time, of course, in AdS5, but the second leg of the light cone coordinates to be exactly this angle phi on the great circle on S5. So this is the combination x minus and x plus. These are the associated momenta. And now the light cone gauge condition is exactly x plus is equal to tau and p plus is equal to 1 in this case, which determines now the length, the extension of sigma by consistency, because the total p plus charge is then just given by r times square root of lambda over pi. So that tells you how the length of the string is related to p plus and square root of lambda. So going back to the gauge fixed going back to the Lagrangian, implementing these gauge conditions. So first of all, these were the two constraints which I now being thinking of it of being fulfilled, just set equal to 0. The coupling to p plus is a total derivative due to the constant due to the choice of setting p plus equal to 1. P minus is the light cone Hamiltonian, and these are the transverse degrees of freedom. And what you now have to do is you have to express the plus and minus coordinates and momenta in terms of the transverse ones. And for this, you solve the constraints. So the constraint C1, which was essentially p dot x prime, written in light cone coordinates and light cone gauge, gives you an expression for x prime minus, which is this. And of course, if you integrate it over the closed string world sheet, this gives rise to the level matching condition later on in the quantum theory. The Hamiltonian, or the light cone Hamiltonian p minus, arises from the second constraint, which is a quadratic equation for p minus. Here you can see if you would have a flat space, this metric component would be gone, and this one, and that's how you get the usual simple flat space light cone Hamiltonian. Here you get, in general, you get a square root form, and it's of course a rather involved expression. And this is now the reason for the choice of the lambda scaling, because here you now see in this way of doing things, there is no lambda dependence in the Hamiltonian. Right, so the gauge fixed action then takes this form. So we learned the extent of the string world sheet, how it depends on p plus and square root of lambda, and we have now for the bosonic theory a square root expression sitting here, which I don't even write down because it is so complicated. And in order to make advances, in particular, if I want to study what I want to do, the quantum theory, I need simplifying limits where I start out with a free Hamiltonian and have an interacting system coming in a higher and higher order expansion. So one needs simplifying limits. One limit which is actually does not have this. It still maintains the full interaction structure, but it sends. So you take p plus to infinity, keep lambda fixed. So this is, if you wish, this is a limit where you decompactify the string world sheet. So the theory now lives on a two-dimensional plane, and this is exactly the reason where you can cleanly speak of asymptotic states and S matrix, and you can make contact to the infinite length limit of a spin chain in gauge theory. Another well-studied limit is the plane wave limit, or the near plane wave limit, which I'll also comment on later on. There you keep this combination of lambda and p plus fixed. So the extent of a world sheet is fixed, and you expand in the large p plus limit, which, as we will see, turns into an expansion of a number of fields of that Hamiltonian up there. And there you have a very controlled quantum theory, which you can study, and which we will do. Another set of limits is the near flat space limit. So you take lambda to infinity, but lambda 1/4 over p plus fixed. There are actually two flavors of this. One is the true near flat space limit, which limits the flat space, which is due to Gopser, Klebanov, Polyakov, the first results there. And then there's the Maldacena-Swanson limit, which Thomas Klose was talking about, which only takes the left moving or right moving degrees of freedom, and not under full control yet. Mostly applies, or it applies to this piece here. Good. So one more comment on the world sheet momentum. Of course, the action is invariant under shifts in the sigma coordinate, and the associated Noether charge is what one should call the world sheet momentum, which is spelled out here. Making use of a constraint C1, we see it's just x minus prime. So the world sheet momentum is just given by the differences of the x minus coordinate on the two ends of the string. So delta x minus. Of course, as I said before, this is the same relation arising for the level matching condition. So the level matching condition just states that there is vanishing world sheet momentum on the string. But And this condition here corresponds exactly to the vanishing of a total magnet momenta in the spin chain language, which we find in the gauge theory. But as I might be able to discuss later on, if you consider the quantum theory, it is actually necessary to drop the level matching condition in the quantization process. So you quantize the system, and then only thereafter you impose the level matching condition. So you have to study the theory in a sense off shell when this condition is violated. Good. That was what I wanted to say to the bosonic story. So now I want to introduce you how to incorporate the fermionic degrees of freedom, and this will be done with the help of this super coset model, which is also the joint work with Maria Zamakla and Sergei Frolov. And we've seen this coset before here in this talk. So this is our little friend. So what is PSU 22/4? The way to describe it is consider a supermatrix with AD being bosonic 4x4 matrices, even 4x4 matrices, and X and Y odd fermionic 4x4 matrices, which obeys these conditions here. So its supertrace vanishes. There's a reality constraint which tells you that A is in SU22 and D in SU4, and which also relates the fermionic degrees of freedom in that matrix. And so the bosonic subalgebra is SU22, SU4, but also U1, because the identity obeys all these constraints. Its supertrace of the 8x8 matrix of supertrace also vanishes. So PSU22/4 is then SU22/4, where I mod out this U1 degree of freedom. And it cannot be represented by supermatrices. This supergroup has a Z4 grading, which you see here in terms of this automorphism spelled out here. So omega of M acts as follows with a certain 4x4 matrix K, which allows for a Z4 grading of any element of PSU22/4 into even and odd pieces 0, 2, 1, and 3, where these indices up here refer to the eigenvalue of this automorphism, so spelled out here. And M naught exactly spans the SU4,1 plus SO5, piece which we want to divide out. So the action will be built only with elements of M2, M1, and M3. And this is achieved as follows. So we pick a group element and write down its current, like this here, and then we only use the A2, A1, and A3 pieces to build the superstring action, which is due to Metzaev and Seitlin. So this is then the kappa symmetric invariant superstring action. So gamma is our old friend, epsilon is the antisymmetric tensor. So what you have to do now, if you want to put your hands on this model, you have to pick a parameterization of G. And as we are heading for a light cone gauge, it is convenient to pick a parameterization where you explicitly, where you consider a product of three supermatrices, where the first one only depends on T and phi, the coordinates which we picked for the light cone coordinates x plus and x minus. Then you have a transverse piece sitting here, certain parameterization, and also for the fermions, which looks like this. This is, of course, a choice, but this choice turned out to be rather convenient. So next step is you have to fix the kappa symmetry, which expressed in the supermatrix language is a commutation or anti-commutation property of your fermionic supermatrix with these sigma matrices. A bit technical. This sigma was essentially gamma 5. And so the upshot is that the theta matrix has 4 plus 4 complex fermionic coordinates, eta and theta. And this choice exactly halves, as you can see, halves the degrees of freedom of that matrix. Good. so now, in principle, I have everything parameterized, and I go through the same procedure as I was showing you in more detail for the bosonic string. And then you end up with a light cone Hamiltonian and a gauge fixed action of that system, where you have here are old friends the transverse bosonic degrees of freedom, and then you have also fermionic degrees of freedom. And again, H is an even more complicated but explicitly known expression, which, if you want to analyze further, needs to be simplified by taking adequate limits. And that's going to be now the second part of my talk. So, taking the near plane wave limit of this expression and confronting it with beta equations. So this is how far we got, plus firms again, and I don't want to be too explicit here as well. So now I do a bunch of rescalings in order to bring, first of all, these boundaries here to a standard form. So just running from minus pi to pi by rescaling sigma, and then I also rescale the fields p and x, which by p plus, and then keep the large p then take the large p plus limit by keeping this combination lambda over p plus squared fixed. And this is the near plane wave limit, because in this limit one sees that the Hamiltonian turns into, in leading order, just a contribution from its quadratic pieces, which is exactly the plane wave light cone Hamiltonian, the Hamiltonian of a plane wave light cone string, and then you have corrections in 1 over p plus of higher and higher orders in the fields. So explicitly, I've spelled it out here. So this is the bosonic piece. It's like you have these mass terms here, and this is the fermionic piece, quadratic. And then the quartic terms are actually not that bad. In the pure bosonic sector, this is what you find, and in the pure fermionic sector, this is what you find. So there is an anti-symmetry with respect to exchanging the transverse AdS5 and S5 degrees of freedom here. And the mixed term, there's also a mixed term, 2 Bose, 2 Fermi, is more involved, which I just spell out here. Okay, so now you can go ahead and perform a perturbative quantization. But in order to do this, it's good to change variables once more and go into complex fields for the transverse bosonic degrees of freedom, because they will then carry clean charges under S1, S2, J1, and J2, which are spelled out here. And then you diagonalize H2 by going into a mode expansion, so you have alpha and beta modes, which describe your free theory. So this is the free Hamiltonian. These are the bosonic oscillators. You also have similar objects for the fermions, of course. And you create physical states by acting with the creation operators on the vacuum, with the condition that the level matching, with the necessity that the level matching condition is obeyed, so that the sum of all mode numbers is 0. And then the leading energy shift delta p minus to this free Hamiltonian can be computed very simply by the Born term, by just taking your favorite state and sandwiching it between the interacting pieces of a Hamiltonian. And that was the starting point for this paper from this year with Sundin and Hensche, because what we wanted to do is we wanted to use this result here and the energy shift in order to test the beta equations, the conjectured beta equations for the AdS CFT system in larger sectors, so going beyond rank 1. And this is, of course, then a test of a quantum integrability of the string theory. Right. So this is what I want to discuss now. So here is the full set of beta equations, which never fits on one transparency. You always have to use tiny font size to get it on. So this is due to Weisert and Staudacher. This up here is the total momentum vanishing condition, and then you have this nested set which is spelled out here in its full glory. The red factor is the famous dressing factor, and it moreover depends on two free variables, eta1 and eta2, which can take either the value +1 or -1, and corresponds to 4 different choices of Dinkin diagrams for this supergroup. And what we want to do now, I mean, there are 2 things. So first of all, we have to understand how to translate these equations into the light code language, and then how to translate string oscillator excitations into these Dinkin labels. So so how many of these nodes K1 through K7 are excited given a certain excitation of the string of a quantum string, and then you also have to solve these equations, of course. So the first step is how to rewrite them in a light code language. And the problem here is that the string does not know this quantity L, but it knows the quantity P+. So I have to re-express one in terms of the other, and this is done as follows. First of all, L depends on the charge J and the number of the Dinkin excitations K in this fashion. We had picked these coordinates P+ and P-, and all I have to do now is I can by making use of these relations, I can eliminate L and J in terms of these by using these equations in terms of P+ and the energy shift delta D. So that's the new thing. I have to feed the energy into the equations. And we are interested in doing this in the near plane wave limit, in which the beta root x4 has this expansion for large values of P. And the remarkable relation which one has in rewriting these equations now is that by including the first correction to the dressing factor in this limit, this combination here is actually equal to 1. And the first correction starts at order 1 over P+ to the cubed. If you include the next correction, so the Hernandez-Lopez term, this exactly acts at this order, but it doesn't kill it. So there is a true 1 over P+ cubed correction, unfortunately. But using this rewriting, then although it doesn't look that way, the central K4 equation simplifies drastically. Because what I lost is I lost this dressing factor piece here, and I also lost these 1 minus 1 over G terms, which it's unfair because they're much smaller, but these terms are gone and these terms are gone. And I get a couple more shifts up here. So this is then the set of equations you have to solve in order to find the energy shifts. So this is simplest for the rank 1 sectors. So SU2 would be a string excitation which only takes these alpha 1s, and the set of beta equations is then this one here. Particularly nice is the SU11 sector, because there the right-hand side of the beta equation is just trivial, just 1. So it's a set of 3 fermions, and the SL2 sector is down here. It's actually just the inverse of this S matrix here. And these sectors you can solve explicitly for any collection of n's, so any excitation number. If you want to go to higher sectors, you have to deal really with a nested structure, and for this it is important to translate this is an awful transparency, I know, to translate the string oscillator excitation structure to the excitation structure on these Dinkin nodes. And this is the translation scheme. So first of all, you have to commit yourself to a choice of eta1 and eta2, and then you know whatever you want to do, you consider a certain string excitation sector, and then you can read off how many Dinkin labels are excited in this table. And doing this, one now can can perform this comparison. On the one hand, you explicitly diagonalize the interacting piece of a string Hamiltonian H4. And on the other side, you explicitly solve the light cone beta equations. And these are the tests that have been performed. So for rank 1, this, as I said, works for arbitrary Magnon number, K4, in these sectors. For SU12, which has this excitation pattern now, alpha 1 and theta 1, this is the first time you have some nestedness in your beta equations. This has been checked for K4 smaller than 3. And the higher the rank gets, the harder the checks become, of course, because solving these beta equations is really, really complicated. Once you spread out. I was very surprised how complicated it was. I thought we could go much higher when we started this project. So here smaller than 3, and there we actually only could test K4 equal 2. But nevertheless, I think it's fair to say that this is a non-trivial test of a quantum integrability of the AdS 5 cross S5 string. Yes, good. So I do have some time, so I can also speak about the algebra, which is joint work with Gleb Arutyunov, who unfortunately couldn't come because of visa problems, as far as I heard, Sergey and Maria. So so how can we understand the symmetry structure of the light cone gauge superstring? So first of all, the global symmetry algebra, PSU22/4, is encoded in a supermatrix Q, which takes this form. And here again, the choice of parameterization of the coset turns into this very nice structure that the x plus and x minus dependencies sit to the left and right of the transverse degrees of freedom. And the various generators of PSU22/4 are then projected out by picking suitable matrices M and taking its supertrace. In particular, the light cone Hamiltonian is part of the structure. So if I take this matrix sigma plus, which was gamma 5 and gamma 5 on the diagonal, you exactly get the light cone Hamiltonian. And there are, of course, all the other generators can be produced in a similar fashion. But this structure also is quite helpful in understanding the subalgebra of PSU22/4, which leaves the Hamiltonian invariant, so which is a symmetry of a light cone gauge theory. Namely, if you look at charge conservation, you see that exactly these charges, which are independent of tau, because x plus is equal to tau in this, independent of x plus, because in our gauge x plus is equal to tau, are the ones which leave the Hamiltonian invariant. So this should be a blue H here. Sorry. So this is how you can classify your charges as the ones which commute with H and the ones which do not. Simply looking at their depends on x plus, if they depend on x plus or not. And you can further classify them in terms of kinematical charges, which are independent of x minus, and dynamical, which depend on x minus. Yeah. And so here is the structure of these matrices M, which I feed into the supertrace here in order to extract the generators. And it is exactly the second. So yeah, the colored ones, which are independent of x plus. So these are the charges which commute with the Hamiltonian. The Hamiltonian is diagonal, and this exactly gives you the SU2/2 plus SU2/2 structure, which has always kinematical and dynamical pieces in it. So the bosonic generators are kinematical, the fermionic ones are dynamical. Right, and the uncolored things are the generators, which are the symmetries which are broken by the light cone gauge. So here is the SU2/2 algebra. We have the bosonic SU2 generators and the two fermionic ones, Q and Q bar, and the central charge. And it furthermore allows this particular supersymmetry algebra allows for a central extension in terms of two central charges C and C star here, which are exactly related, which have been shown by Beiser to arise in gauge theory and being related to the Magnol momenta of a chain. And the question one can now ask is, of course, is there a central extension in string theory which also arises? And that connects to the worldsheet momentum, which I was introducing at the very beginning. So I have to rush a bit through. So just if you look at an explicit at the explicit expression for these charges, because we now have these, right, in terms of these parameterizations. I also told you that the supercharges are the ones which explicitly depend on x minus, are dynamical, and it turns out that this dependence due to the structure we used up here in parameterizing things, this factorization here, just the x minus dependence factorizes into this prefactor e to the I x minus, and these are all transverse degrees of freedom. So if you then compute the QQ anti-commutator, you can actually you can see that the x minus dependence is inert up front, and here you at least in leading order and next to leading order in classical theory and leading order in quantum theory, what you get is exactly the level matching condition here, the p dot x prime, and then you can integrate this, and you see that you get exactly this shift in the worldsheet momentum. So exactly the difference between x minus at one end and x minus at the other end of the string worldsheet. So this is how you see how the supersymmetry algebra of a light cone string becomes centrally extended once you go off shell. And it's nice to see this parallel structure to the gauge theory. Right. So this should bring me to my end. Yeah. Good. So in this talk, I introduced you to the uniform light cone gauge for the AdS 5 cross S5 string, and the upshot was an exact gauge fixed Hamiltonian for this system, including all the fermionic degrees of freedom. And I then discussed its perturbative quantization in the near BMN limit and determining its spectrum at leading order in 1 over p plus. And I then confronted this spectrum to a set of to the conjectured set of Bethe equations for the AdS CFT system, which I had to rephrase in a light cone language, where some simplifying structures arose. And finally, I showed you how the off-shell supersymmetry algebra of the light cone superstring gets centrally extended. Thanks.
I have one comment. I think in the second paper you mentioned, many of the structures you discussed are in the earlier paper with Rashatsky and myself, and see if I can how. I don't know. I'm not sure exactly what is different. The C4 structures and the construction of the action. It's actually not Mitzayat in the one.
Okay. So it's not the action, but it's the set 4 grading and these.
Set 4 grading and actually the action also. They wrote the Western term in a different form. They didn't write it using. They wrote it in a much more complicated form.
Okay.
The other question was, in light cone gauge, normally normal ordering is the thing that gives all the subtlety.
Mm-hmm.
Is there any? Have you looked into the normal ordering?
Well, that's a very central issue once you go to the next two leading order. So if we would go to the H6 terms, so this was H4, so fourth order in fields. There are no normal ordering ambiguities, but when you go to H6, that really becomes essential. Also, when you want to study the SUSY algebra.
Just to understand it, so usually if close to light cone algebra, I would have thought that already at fourth order.
In principle, yes, but you're safe because we do a certain. Okay, so H4 is free of P. There are no P degrees of freedom because we did a certain change of variables in the classical theory. And I think if you would worry about these terms, they should cancel out. I think there will be no contribution, but it will be central if you go to the next order. That's clear.
Any questions?
Thanks very much.